Hello, free calculus. Welcome back here, 7.3. We are now talking about hyperbolas, otherwise known as hyperbolas, but no one says that except for me. There you go. Here's a hyperbola. This is when we slice our cone like almost straight vertically so that we hit both the top nap of the cone and the bottom nap of our double napped cone. And then we need to define what the locus is we need to define a hyperbola, and it is defined as the locus of points. So all the points such that the difference of the distances from any point on the hyperbola to two fixed points, just like we had for ellipse, where we had those two fixed points that were foci, we have foci again in hyperbolas. This time, though, instead of the distance between those two being d1 plus d2, they're now going to be d1 minus d2. And that's going to stay constant for all points on our hyperbola. Just like we had for ellipses, we had horizontal ellipses and vertical ellipses. For hyperbolas, we have the same thing. We have horizontal hyperbolas and we have vertical hyperbolas. So horizontal hyperbolas are kind of like two horizontal parabolas opening up back to back, and verticals are like two up and down parabolas opening up back to back. So open left or right, they're opening up towards that x-axis. Vertical, they're opening up and down towards that y-axis. The center HK is going to be the midpoint of our foci. So we go halfway between our two foci, we'll get to the midpoint. That midpoint is the center, which is HK. The vertices, which are our turning points of our parabolas on either side, are plus or minus a units away from the center. So here is one foci, here's one foci, right? If we just had one of them, it would be the focus for a parabola. But I have two of them, it's a hyperbola. These guys are called foci. Halfway between these two is the center. The distance between the vertex of each of these parabolas on either side and the midpoints, or the center, is called A. And then the co-vertices are plus or minus B units away from the center. And these co-vertices are on this axis here, and we're going to talk about what that axis is in just a second. So that's our vertex, right? This guy down here is my co-vertex, or co-vertices. The distance to my co-vertices is B. All right, and then we have two axes that we have in hyperbolas. The transverse axis connects the vertices and has a length of 2a. In other words, a plus a gives me my transverse axis. It's just this piece here between the two parts of my hyperbola. So not all the way out to the focus, just from vertex to vertex, that's my transverse axis. And so then we have a conjugate axis, and it connects the co-vertices, and it has a length of 2b. So b plus b is going to have a length of 2b, my conjugate axis. The asymptotes are the diagonals that diagonal lines that are like guidelines for the curve. They're not really a part of our hyperbola, but they guide how wide our parabola shapes are on either side. And they guide the curves. The foci are plus or minus c units away from the center, just like they were with ellipses. So this big distance here, all the way to here, is your C. Same thing on the other side. So this is your focus. This is your center point here. Covertex are on your conjugate axis. Vertices are on your transverse axis. This time our formula to find C, though, is going to be C squared is equal to A squared plus B squared. So what's going to be tricky is you're going to take a conic section test, and you got to remember, all right, I've got a hyperbola. This one is a squared plus b squared. Or I'm working with an ellipse, so this one is a squared minus b squared. So that's what's going to be challenging is when we put this stuff all together. Standard form looks very much like an ellipse. So x minus h squared over a squared, y minus k squared over b squared equal to 1. And again, this is for our horizontal. What is different about this one than with the ellipse? You see what the difference is? The difference is the sign in between the x's and the y's, right? In ellipse, it's x squared plus y squared. For our hyperbolas, it's a negative sign in here. All right, so then for our vertical sign, it's going to be, because order matters for this one, it matters whether we have the x first or the y first. So for this one, it's going to be y minus k squared over a squared minus x minus h squared over b squared is equal to 1. All right, so just like before with the ellipses, the bigger denominator is going to go with the x's if I'm horizontal or the y's if I'm vertical. Unlike the ellipse we always had x, y, and it was positive. But because we're negative sign in there, that means order matters. So I always put whichever has the a squared, whichever has the biggest denominator is going to go first, and then we're going to subtract off the one that's the smaller denominator. All right, our transverse axis is always going to be y equals k for horizontal, or x equals h if we are vertical. And it's going to be the opposite of that. Our conjugate axis is x equals h for horizontal, y equals k if we are vertical. And then we can find our asymptotes using these formulas. Y is equal to plus or minus b over a, x minus h plus k. This is if it's horizontal. And if we're vertical, it's y is equal to plus or minus a over b, x minus h squared plus k. I think we are missing, we're adding a squared here, and I don't believe that needs to be there. All right, there you go. So we can look up here just to see why are these the case. So look up here with our vertical, our horizontal axis, our horizontal hyperbola, transverse axis is this guy here, right? And that's at x is equal to k. Sorry, y is equal to k because it's a horizontal. Which axis are we crossing? We're crossing the y-axis at k, so it's y equals k. For our conjugate axis, we're now talking about this vertical piece here. That's a line that's crossing the x-axis at h. And so that's how we get this x is equal to h. Opposite is true for our verticals. On the next video, we're going to start graphing hyperbolas, and we're going to have lots of fun.